Hey there, I'm srcmake, and in this video we will look at the interview questions finding the lowest common ancestor in a binary tree and a binary search tree. We're going to do both of those questions in this one video. So in this video we are going to look at the terminology to see what a lowest common ancestor is. We are going to look at the easy Leetcode problem for finding the lowest common ancestor in a binary search tree, and I've got this diagram here that we are going to go over. Then we are going to look at the iterative solution to that problem, and I've got some stuff here for how the algorithm works. And then I've got some C++ code written here that we will go through, and I will run it on Leetcode to make sure that it works. After that, we'll talk about the time and space complexity to make sure that it's the best answer. Afterward, we'll move on to the harder question, which is a medium Leetcode question, finding the lowest common ancestor in a regular binary tree. I've got another diagram here that we're going to go through. We are going to do the recursive solution for that one. We're going to talk about it a little bit. Then we've got some more C++ code here. And if you don't know C++, it's really fine because this is basically pseudocode at this point with how easy I wrote it. Then we're going to run that solution in Leetcode, make sure that it works, compiles, that it's good. We're going to talk about the time and space complexity of that one, and that will be it for this video. So all of this pseudocode will be right here on this webpage. If you need to get to this webpage after the video, which I really recommend because you should look at the code afterward, I'm going to try to make this a quick video. Click the link below and you can get to this page. And while you're down there, hit the subscribe button for this YouTube channel. Thanks. So finding the lowest common ancestor in a binary tree. A common ancestor for two nodes is a node that has those two nodes as descendants. And so, for example, if we've got this binary search tree right here, and we've got these two nodes, P is node 3, Q is node 1. If we look up this tree, we can see for Q, its ancestors are 2 and 6 getting on the way to the root of the tree. And for P, its ancestors are 4, 2, and 6. And so the common ancestors between nodes 3 and 1 are 2 and 6 because both of them have those as an ancestor. Now the lowest common ancestor is going to be node 2 because it's the node that is closer to P and Q, nodes 1 and 3, that also happens to have the common ancestor constraint. And that's kind of the definition you should know it in case an interviewer asks. And so we'll answer the easy Leetcode question, find the lowest common ancestor in a binary search tree. So let's look at the iterative solution. The first thing that we care about is the lowest common ancestor. The trick to doing this is it's the node of P and Q that has one of the following properties. The current node, the answer node, is P and Q is on the left of the subtree. The node is P and Q is in the right subtree. The node is Q and P is on the left, or the node is Q and P is on the right. And the other condition, which is the one from this diagram, is that P is on the left or Q is on the right, or vice versa. And so, like this example right here, 2 is the lowest common ancestor, and Q is on the left and P is on the right. So those are the 5 conditions that will mark a node as being the lowest common ancestor of two nodes in the tree. And so for this particular solution, we're going to take advantage of the search property of binary search trees, where in a binary search tree, every single node, the left children are less than the value of the node, and the right children are greater than the value of the node. So for example, in this tree, we've got node 6. All of these nodes are lower than 6, and all of these nodes are higher than 6, the values. And that's true for every single node in the tree. For example, node 9 has 7 and 8 to the left, and 10 and 12 to the right. 7 and 8 are lower than 9. 10 and 12 are larger than 9. And so that lets us not have to look at the entire tree because we know where we need to go. So, for example, in this tree, we will start at node 6 and we'll say, oh, we're looking for node 3 and node 1. Where is node 3 and node 1? They're going to be in the left subtree. We don't even need to check the right subtree because we know that those are both on the left because of the binary search tree properties. So if we look at the solution here, we've got one function, lowest common ancestor. It accepts a root, node P and node Q, and the iterative solution is to have a while loop. So we create a temporary tree node variable that points to the root to start out with, and we've got a while loop that continuously traverses the tree. By the way, that's how iterative solutions work for linked lists and trees. So this is just a common syntax. Make note of that. So we've got really simple code in here. if P is on the left and Q is on the right, or vice versa, or if this node's value is equal to P or Q, that's what these two blocks in the if statement are, then this node is the answer, and so we return that. Otherwise, we need to look deeper down in the tree, and so which way do we need to go? Well, if P is on the left, then we look at the current node's left subtree. Otherwise, P has to be on the right, and so we have to check the right subtree, so we look at the current node's right subtree, which is going to its right child. And so that is basically the solution. It's actually really simple code. I recommend looking at it afterward or trying to code it yourself. I'm going to copy this code. This is good enough right here. And I'm going to paste it into Leetcode. This is the problem. If you need to get to this problem, there is a link right here for you to get to this page afterward. So I'm going to run the solution to make sure it compiles fine. And fingers crossed, it does. I'm going to submit it so we can run all the test cases on Leetcode. You can see I was trying this out earlier. And we've got 83% of the time. But earlier when I did it, I got an even better time, and it was like 90-something%. So this is the best solution. So looking at the time and space complexity of this solution, the time complexity is order n because we will at worst look through each one of the nodes in the tree. And it's specifically order h, where h is the height of the tree. Since it's a binary search tree, we know exactly where we're going, and so we're going to continuously be going down the best route of the tree until we find the lowest common ancestor. So it's order h of the tree. The space complexity is order 1 because we don't really use any extra space. You can see that in our code, the only thing that we have besides the tree itself is this temporary variable for what the current node is, and that's constant space. So the reason we did the iterative solution and not the recursive solution is because the recursive solution has a space complexity of order n. The code itself is basically the same, but when you do the recursive solution, you look at the root node, and then you look at the next, and then you look at the next, and it turns out that you might have the entire tree within memory, and so that just takes computer science stack space. Not the data structure, because the data structure we'll talk about next, but it takes the application stack space, which is why it would be order n, which is worse. So moving on to the medium Leetcode question, finding the lowest common ancestor in a binary tree. It's basically the same question as before, but this time we have a binary tree instead of a binary search tree. So a regular binary tree means that there's no special ordering in this tree. You can see we've got node 5 right here, and on the left we've got greater and less than nodes 2 and 7 are both greater than and less than 5, so there's nothing special, which means we might have to check the entire tree at worst. There's no special thing we can do to do a smart search on the tree. And so if we look at the recursive solution, we see the exact same thing as before, the conditions where the current node is P or Q is on the left, the current node is P, Q is on the right, etc. That is going to determine how we know which node is the lowest common ancestor. But the thing we have to do here that's a little bit different is in our search, we are going to do this recursively, and basically we're going to recursively say for each node, recursively check the left and right subtrees to determine if either one of those subtrees has P and Q in it. And so here's what's going to happen. We're going to do a recursive solution, and there's two things we need to keep track of. One is the current node the answer? Is it the lowest common ancestor? That's what we need to keep track of by doing this. The other thing that we need to keep track of is a Boolean, true or false. Did we find P or Q as a descendant of the current node? When we check the left and right subtree, or if this node itself is P or Q, we need to return true if that one of those cases is so. So let's look at the actual C++ code. We've got a function, a lowest common ancestor, that you pass in the root P and Q. We create this answer tree node variable that we are going to hopefully fill up with our recursive function. We call the recursive function, and at the end of it, we don't really care about what happens to it. We just want to make sure that the recursive function fills up this answer so that we can return it properly from this function. So what about this recursive function? So our recursive function, as I said, returns true if the current node is P or Q or has P or Q as a descendant. And so what we pass in is the current node, P, Q, and the answer that we might mark, or that we want to fill in. And so what we do inside of this recursive function is we say if the current node is null, return false, returning false because this node obviously is not P, it's not Q, it does not have P or Q as any children because it's null. So then what we do next is we look at the left subtree by recursively calling this function on the current node's left child. We recursively call this function for the current node's right child, and these return booleans. And so then we have this little if statement here that's basically the same as the last problem, but it's basically the same as this right here. It's just written out in code. So the conditions are either the left subtree had P or Q and the current node is P, the left subtree had P or Q and the current node is Q, and you continue on with those situations for the right subtree having P or Q and the current node being P or Q. And then maybe it's possible that the left subtree had P or Q and the right subtree had P or Q. And if any one of those conditions matches, then this current node is the answer. It's the lowest common ancestor. And so we just mark the answer there. Besides that if statement, the other thing I said was that this has to return true in certain cases, and this function will return true if the current node is P, if the current node is Q, or if the left subtree had P or Q or the right subtree had P or Q. And so that is actually it. That's a really simple, the code is actually really simple. Intuitively, it might not seem that easy, but it's basically the same property that we talked about before. And it's actually not that bad. Like, it's actually pseudocode, so this is really easy code to write. So what I'm going to do is I'm going to copy this. I'm going to come over to Leetcode, the medium question. We're going to run this code, make sure it compiles. Oh, you didn't see that I hit run code. So we're just making sure that it compiles. It got accepted, so I'm going to submit the code so we can run all unit tests. You can see that I did this problem before. And 99%, 12 milliseconds, it's really great. So this solution is great. So this solution, the time complexity, is order n because recursively we visit every node exactly once at worst case. That's as good as we're going to do because there's no special searching like binary search trees. And then the space complexity is order n because potentially we hold the entire tree in the stack, the application stack, because recursively we have to keep adding things into memory. And so the reason we chose the recursive solution here is because the code is simpler. The iterative solution is harder because it actually requires a stack data structure to keep track of which nodes you are visiting. And so that's it. Those were the two questions, finding the lowest common ancestor in a binary tree and a binary search tree. I really recommend coming to this page and bookmarking it in case you need to see the code later, and make sure you can actually code it yourself because it's really important to write the code and making sure you know how to actually write this all out. So if you want to see any other interview questions, please leave a comment. Feel free to like this video and make sure you subscribe. I'm srcmake, and thanks for watching. Good luck in your interviews.